Hello, my name is Kevin Smith and I'm an Agilent Applications Engineer. Today, we're going to take a look at some logic analyzer basics for Agilent logic analyzers. This is the first in a four-part series, and we're going to take a look at setting up an acquisition for both asynchronous timing mode and state mode. So currently we are looking at the Agilent Logic Analyzer GUI. We have a 16910 card, but this is going to be very similar for all of our Logic Analyzer cards. And all of the acquisition setup is basically contained on the individual Logic Analyzer module. Okay, and we want to start by clicking on the sampling setup or the bus signal setup. So if we click on the buses signals, and note we can get back and forth to the sampling tab and the bus signal tab, it pretty much defaults to something like this. The first thing that's worth pointing out is that there are activity indicators. I'm already connected to a device under test, which is an 8-bit device, and because it has little up and down arrows, and it's indicating that there is activity on this bus. All these little low guys, these flat lines, indicate that there is no activity, or that they are stuck low. Sometimes you'll see them up top. And depending on how many logic analyzers you have, or channels you have, they're going to be grouped into 16-bit pods. Okay, and we can simply add more bits to a given bus, by clicking on them. Okay, or by left-clicking and sliding the mouse along. Since this is an 8-bit bus, we'll just stick with these guys. We could add a bus simply by right-clicking on the bus signal name area, specifically on the name, and add a bus or signal. We can name it. If we just click OK, we get a new one, and simply add bits like that. All right. Now, if we slide this all the way over, we can also see that there is one clock. All right, and we should probably add that. All right, but since we don't really have anything going on this on my bus 2, we're going to delete him. Okay, but now we have added a clock to my bus 1 as well. It's also a couple of important things to note. Okay, that we can quote assign channels. Okay, the default channel is basically MSB first. Okay, but we can swap that to LSB first, essentially. We'll keep it back the way it's going to be. Also switch big endian, little endian. It's also important to note that we can add individual names to channels. Simply hit 1, for example. We don't really want to do that. And we can look also, it's important to note that we can enable channel order selection. All right. So for example, if I wanted to switch these 2 bits for some reason, okay, swap a few bits, I've enabled channel order selection, and now it goes 0, 1, 2, 3, 4, 5, 6, then 7. Okay. But really I don't want to do that. And we are going to disable that. And you'll notice that you can right-click just about anywhere and get a new menu. It's also important to point out that to adjust the thresholds. So if we right-click on the threshold setting, okay, we can apply to all pods or not. There's a bunch of very common TTL threshold levels: TTL, CMOS, ECL, and so forth. We can also do user-defined in a 10 millivolt increment. The limits generally depend on are generally up to 8 volts. Okay, we're going to stick with standard, and we can set it on a per pod or per 16 channel basis. So that's the short version there. Again, there's lots and lots and lots that you can do. We can also do, if we look at the display, we can also show the polarity, default base, add comments, or remove, thresholds, activity, channel numbers. So that's the real short version on assigning channels and to various buses. Next, we want to take a look at the actual how this instrument is going to sample the data. There are two basic modes for logic analyzers: asynchronous timing mode and synchronous state mode. Okay, most timing mode is much like a scope. It just samples whenever totally asynchronous to the data at pretty much whatever rate you tell it to. Okay, all MSO scopes support asynchronous timing mode and not state mode. Now, depending on what logic analyzer you have, you're going to have some different options here, but you can get different max sampling rates by going to 500 megahertz at full channel mode, or half channel mode gets you 1 gigahertz. So half channel mode, we literally get rid of or throw away our half of our channels, and the sample period is 1 nanosecond. If we go into full channel mode, we definitely have some more granularity, 2 nanoseconds, 4 nanoseconds, and so forth. We can really slow down that sample rate up to 500 microseconds. Okay. And we'll sample the data totally asynchronous, just a 1 or a 0, 1, 0, 1, 0. In state mode, right? No, we should notice that the sampling options disappear. In state mode, what happens is, whenever the clock goes high, we have some control over that. Whenever the clock goes high, we take a sample. In state mode, you cannot see the clock. In timing mode, you can. So, whenever the clock goes high, we take a sample. And it doesn't just have to be a 250 megahertz clock. In the case of this logic analyzer, it's up to 250 megahertz. Certain options will get you to 450, or in certain cases, with 500 megahertz, it's going to force us into a, quote, dual sample mode. We sample on both edges of the clock, high and rising edge and falling edge. And there is difference between dual sample and master out of the scope of this. Anyway, if we go into the 250 megahertz mode, we can do both edges, falling edge, rising edge, or don't care. And we can have qualifiers on other clocks, which we are not going to use in this example. As far as memory depth is concerned, okay, the standard memory depth on many logic analyzers is at least 1 megapoint, or 1 megasample per channel. The memory depth is always on a per channel basis, okay? And the memory depth is license key upgradable, does not need to return to Agilent. Then there is the how much memory depth with respect to the trigger. Moving it all the way to the left simply means that all of the data will be acquired after the trigger, all of the data before the trigger, or in center, 50% before, 50% after. And then there's timing zoom. Timing zoom is basically a fast, and we have independent control of the memory, very fast sampling. In the case for this particular analyzer, 250 picoseconds, so it's 4 times faster than in state mode. And it's basically just a zoom for 64 K points around the trigger. Finally, we have iScan. This is particularly important for state mode, where we can optimize the sample position with respect to the clock. And there's about 5 nanoseconds on either side of the clock edge. The instrument can auto set this up for you. And each of the modes do slightly different things. Okay, there's getting into detail is outside the scope of this, but can also adjust the threshold levels. So in state mode, particularly as you get faster and faster, this can be rather important. Finally, we're going to look at the trigger. Now, we're in timing mode, so the actual triggers are quite a bit different than you might find in state mode. As it turns out, complex logic analyzer triggering is more of an art than a science. In the information tab below the video, there are I've linked a few app notes there, and if you need complex triggers, you should contact Agilent directly, or take a look at these app notes. So basically, anything means auto trigger. Anything happens, eventually it will trigger and fill memory. Now notice we have all these little chevrons. Okay, there's a lot of flexibility here. We can insert things before, after, negate the if clause. Okay, but a real basic trigger, for example, might be if bus signal, all right, all bits, bit 1 through bit 0 through bit 7 equal, for example, FF, and I can type in this box as well. If it eventually happens, trigger and fill memory, or I can add some previous actions. I can set a timer, a counter, flags, and so forth. I don't want that action, however. Or I can go to a further step, go to next. And then I can, for example, add various other steps, such as wait for external arm. Then I can add yet another step, bus pattern, all bits equal 0, 0. So this scenario, I'm going to find FF, then wait for an external arm trigger to the TTL on the rear panel, the BNC connector on the rear panel in. Then I'm going to look for 0, 0. Then I can trigger and fill memory. And pretty much it's just drag and drops. There are various time qualifiers, branching. All right, the branching, of course, gets very complex with if, then, else if steps. We can also store and recall trigger setups, or just wipe everything out. So let's go back to the if bus signal equals. Oh, notice we also have quite a few choices, including range choices. Let's go back to FF. Okay, and click OK. So real short version is that we've set up the analyzer in timing mode. We've set up our signals, and we've set the trigger. Now it's time to run. This little button here means run, and this little button means run repetitive. It will just keep triggering and displaying data. We can also set from the run stop menu, run properties. Okay, we can save after every acquisition. This will result in files being stored to the local hard drive. Okay, with the name. You can auto increment the files and stop running after so many acquisitions. The one key point here is that when we do this, there is always dead time while the logic analyzer is saving the data to the hard drive and then rearming. At this point, though, we should just click the run button and acquire some data. Notice that the logic analyzer takes some time to initialize. It's acquired data, and it saved it to disk. I'm going to turn that off. Run properties. Okay. But notice now, if we run again, it doesn't have to reinitialize, but it will if we switch to state mode. This concludes part 1 of Logic Analyzer Basics. Please see part 2 analyzing data. Thank you for your attention.